Welcome to the deep dive. Today we're digging into, well, a cosmic detective story,
Oh,
really.
yeah.
It's this century-long quest to figure out something that sounds simple. How much does our Milky Way galaxy weigh? And, how big is it actually?
It's funny, isn't it? Seems like such a basic question about our own galactic home.
Right. But it's been a real puzzle for, nearly 100 years.
It has. And as the sources we looked at show, a big key is this idea of galactic escape velocity.
Escape velocity. That sounds important.
Definitely. Think of it like the ultimate speed limit for anything trying to leave the galaxy.
Okay, so galactic escape velocity. That's the speed a star or whatever needs to hit to actually break free from the Milky Way's gravity.
Exactly that. Like launching a rocket from Earth. Gotta hit that escape speed to get away.
Makes sense. So how does that tell us about the galaxy's mass?
Well, the stronger the gravity, meaning the more mass of the galaxy, the higher that escape speed needs to be. So if we can measure that speed.
We get a handle on the mass. Got it.
And some of the earliest folks looking into this, like Jan Oort, way back, he pointed out something pretty smart.
What was that?
He said, look, it's probably really unlikely we'd see tons of stars just zooming out of the galaxy at super high speeds.
Yeah, that seems logical. Our galaxy would be, falling apart if that were common.
Right. But the big challenge, and this comes up a lot in the research, it's that measuring how things move within the galaxy doesn't easily tell you about the mass way, way out in the halo.
The halo. That's the big sort of diffuse sphere of stuff surrounding the main disk.
Exactly. And most of the mass, especially the dark matter, is thought to be out there. Our usual measurements are kind of insensitive to that outer region.
So it's like trying to weigh, I don't know, an entire iceberg just by looking at the tip.
That's a great analogy. So for a long time, the main idea was pretty basic.
Okay.
The escape speed right here near our sun must be faster than the fastest star we actually see nearby.
Okay, yeah. If a star hasn't escaped, it can't be going faster than the escape speed. Seems straightforward.
It does, but, there are always complications.
Ah, the caveats. Like what?
Well, the sources mention things like stars that aren't actually bound to the Milky Way, maybe they're just passing through, part of the wider local group.
Our galactic neighborhood, right?
Yeah. And then you have these runaway stars kicked out of binary systems at high speeds. They complicate the picture.
Cosmic curveballs. Okay. So how did they try to estimate it back then with these issues?
Early on, people used simplified models. Imagine the galaxy as just like a sphere with stars orbiting at a constant speed out to some edge.
A bit basic, maybe.
Oh, definitely simplified. But based on that kind of model, say back in the 80s or 90s, if you assumed an escape velocity near us of maybe 500 kilometers per second,
Which is incredibly fast.
it is, then, given what they knew about our position and speed, the galaxy's edge might be around, say, 41 kiloparsecs out, and the total mass would be something like 4.6 times 10 to the 11 solar masses.
So 460 billion times the mass of our sun.
A huge number. But then Leonard and Tremaine came along in 1990 with a more statistical approach.
Okay, how did that work?
They looked at the high velocity tail, so not just the single fastest star, but the whole distribution of the very fastest ones.
Trying to get more information from the group.
Exactly. But it was tricky. Their estimates were really sensitive to the exact shape of that tail. Are there lots of stars just almost escaping, or does the number drop off really fast?
Subtle differences matter.
They do, and it also really depended on how good the measurements were for distance and motion for these fast stars. Hard to do accurately back then.
So what did they find?
Their estimates actually varied quite a bit, somewhere between 450 and 650 kilometers per second, a big range.
Yeah, that's a lot of uncertainty. Still, fast car versus jet plane difference.
Pretty much. And they made a really key point, which the research emphasizes.
Which was?
You can't get the total mass of the galaxy just from the escape speed near us unless you know how the mass is spread out way beyond the sun.
Back to the iceberg problem. Knowing the ripples nearby doesn't tell you the whole size.
Exactly. And one source mentioned that before the Gaia mission, the uncertainty in the Milky Way's mass was maybe a factor of 4.
Factor of 4? That's enormous.
It really is. Then came data from the Hipparcos satellite and another instrument, Coravel, in the late 90s.
Hipparcos was a big deal for measuring star positions, wasn't it?
Huge. They looked at lots of stars, and their escape speed estimates came out a bit lower, maybe 440 to 490 kilometers per second.
Lower. Any idea why?
Well, the thinking is that maybe Hipparcos, for all its strengths, might have missed some of the really faint stars that could potentially be the fastest ones.
Ah, okay. Hard to catch the dim speedsters.
Right. One researcher, Mayon, found only about 10 Hipparcos stars going faster than 350 kilometers, which isn't that many at the extreme end.
Hmm.
But later work combined Hipparcos with other data, recalibrated things, and found more fast stars, about 24 over 350 kilometers, the fastest being 458.
So they were closing in on it.
They were. Their conclusion was that the escape velocity probably wasn't much higher than, say, 530 kilometers per second.
Okay, so the picture's getting a bit clearer. What about just before Gaia?
Yeah, estimates from another survey, the RAV survey around the mid-2000s, landed in a similar ballpark, about 530 to 544 kilometers per second.
Consistent then.
Pretty consistent.
Yep.
And importantly, as one source points out, detailed theoretical models of the galaxy, including the bulge, disk, dark matter halo, everything.
The whole shebang.
Yeah. They were also predicting escape speeds around 550 kilometers. So observations and theory were kind of lining up, even if the exact mass was still fuzzy.
Okay, that sets the stage nicely. So then, Gaia arrives.
Then change it.
And the big questions were, could Gaia nail down that escape speed better? Does it change depending on where you are in the galaxy? Does it tell us more about the mass and how it's arranged?
And the answer basically was yes, yes, and yes.
Fantastic. So Gaia gave us much better data on star speeds and positions.
Unbelievably better. Billions of stars. It really opened up a new window. But first, maybe we should clarify what escape speed means in practice now.
Good point. It's not like escaping to infinity, right? There's other stuff out there.
Exactly. So nowadays, astronomers often talk about escaping to the virial radius, usually called R200.
R200. What's that?
Think of it as a sort of practical boundary for the galaxy, based on the average density of the universe. It defines a region where the Milky Way's gravity is dominant, enclosing a mass we call M200.
Okay, so it's like the edge of the Milky Way's gravitational sphere of influence, more or less.
That's a good way to put it. It's a more standard definition used in cosmology.
And I saw mentions of computer simulations, like Auriga. How do they fit in?
Yeah. Those simulations are crucial. They model how galaxies like our own form and evolve. Auriga, for example, has been really good at reproducing features we actually see in the Milky Way.
So they help us test our understanding and interpret the real data.
Precisely. They give us confidence that our theoretical framework isn't totally off base.
All right, let's get to the Gaia results. What's the scoop? The sources mentioned Minari and colleagues in 2018.
Yes, using Gaia's second data release, DR2. They applied that same statistical method from Leonard and Tremaine, but with Gaia's much, much better data.
And they focused on specific stars?
They did. They looked at halo stars that are actually orbiting the galaxy backwards, counter-rotating relative to the sun and the disk.
Why those stars?
The idea is that these stars are more likely to be part of the older, more spread-out halo population, and their speeds might better represent the true high-velocity tail needed to probe the escape speed.
Clever. And what did they find? Is the escape speed constant?
No, and this was a key finding. They showed it decreases as you go further out from the galactic center.
Which makes sense, right? Gravity gets weaker further away.
Exactly what you'd expect. And near us, near the sun, their value was 580 kilometers per second, plus or minus about 63.
580 kilometers. That's even higher than some of the pre-Gaia estimates.
It is, yeah. And using that, along with a standard model for how dark matter is distributed, the Navarro-Frank-White or NFW profile.
That's the one where dark matter is denser in the middle and thins out?
That's the one. They estimated the total mass, M200, to be around 1.55 times 10 to the 12 solar masses. So over 1.5 trillion suns.
Whoa. That's significantly heavier than the earlier numbers we talked about.
It is. And they also estimated how concentrated that dark matter halo is. There's great figure in the sources showing escape speed dropping with radius with their data points plotted. You can really see the trend.
Visuals definitely help grasp that.
Okay.
What about other studies using Gaia, Thiessen et al. In 2019?
Right. They also used DR2, again, focusing on that high velocity tail of halo stars. But they really dug into how the history of the Milky Way, like past mergers with smaller galaxies, might shape that tail.
So, considering the galaxy's formation story.
Yeah. They argued that the shape of the tail depends a lot on the orbits of these halo stars. Are they mostly radial, plunging in and out, or more circular, what we call velocity anisotropy?
Anisotropy. Meaning not the same in all directions.
Exactly. And they noted evidence that halo stars near us seem to prefer more radial orbits, which might be a lingering sign of a big merger event in the past.
The galaxy is still settling down from some ancient collision.
Kind of, yeah. So, using their analysis, also focusing on counter-rotating stars, they got a slightly lower local escape speed, 528 kilometers plus or minus about 25.
Okay. Similar ballpark to Minari, but a bit lower. And their mass estimate.
Their derived M200 mass was closer to 1.0 times 10 to the 12 solar masses, so 1 trillion solar masses. Still huge, but less than Minari's estimate.
So still some variation depending on the exact analysis method.
Definitely. But the key thing was that different teams, using this amazing Gaia data, were starting to converge on values around 1 to 1.5 trillion solar masses, with escape speeds in the mid-500s kilometers. A huge improvement in precision.
And there was one more recent study mentioned, Kapteyn et al., 2021.
Yes, using an even larger sample of halo stars, they aimed for even higher precision.
And did they get it?
They did. Their direct measurement was 497 kilometers with a really small error bar, only about 8 kilometers.
Wow, that's precise. But lower again.
It is lower. However, they suggested their method might have a slight bias, underestimating the speed by about 10%. So they argued the true value is likely closer to 550 kilometers.
Correcting for potential systematic effects.
All right. And after accounting for that, their derived mass, M200, was about 1.1 mina times 10 to the 12 solar masses. Very tightly constrained.
So it really feels like Gaia helped us zero in on a Milky Way mass around, say, 1.1 to maybe 1.5 trillion solar masses and a local escape speed in the 530, 580 kilometers range.
That seems to be where the consensus is settling, yes. A remarkable convergence thanks to Gaia.
It really is. A trillion solar masses. Hard to wrap your head around.
Absolutely. And interestingly, as the sources point out, nailing down this escape velocity has knock-on effects elsewhere.
Oh, yeah? Where else?
In the search for dark matter.
How does escape velocity connect to finding dark matter?
Well, dark matter particles are whizzing around in the galaxy halo, right? And the experiments trying to detect them here on Earth need to know the likely range of speeds those particles might have. The maximum speed a dark matter particle bound to the galaxy can have is set by the galactic escape velocity.
Of course. If it were going faster, it wouldn't be bound to the galaxy anymore.
Exactly. And a study by Wu and colleagues in 2019 found that for searches targeting low-mass dark matter particles, the uncertainty in the escape velocity was actually the biggest astrophysical uncertainty limiting their results.
Really? More than, like, how the dark matter is distributed locally.
For those low masses, yes. Changing the escape velocity could potentially shift the exclusion limits from experiments by orders of magnitude.
That's huge. So our better escape speed estimates directly help the dark matter hunters.
They do. Now, that same study also found that using the best fit value from Monari et al., the 580 kilometers one actually only made fairly minor changes to the existing limits from big experiment like Exion and 1T.
Okay, so it didn't completely rewrite the dark matter map, but it tightened things up.
Precisely. It reduced a major source of uncertainty, making future searches and interpretations more robust. As we get even better escape velocity data, it will further refine our picture of the local dark matter environment.
That's a really cool connection. So let's try and wrap this up. This whole quest to weigh the Milky Way and find its edge. It's been quite the journey.
Almost a century of effort, yeah.
And this galactic escape velocity, this cosmic speed limit, turned out to be a really crucial piece of the puzzle.
Absolutely central.
Then Gaia came along and just blew the doors open, giving us much better measurements, showing the escape speed actually drops as you go further out.
Which makes perfect sense gravitationally.
Right. And now we're converging on a total mass for the Milky Way of somewhere around, let's say, 1 to 1.5 trillion times the mass of our sun.
With escape speeds near us, probably in the mid-500s kilometers, it's a much clearer picture than we had even a decade ago.
It's kind of awe-inspiring, really. Thinking about how we can figure this stuff out just by meticulously tracking how stars move, we're getting a real sense of scale for our own galaxy.
It is amazing. And it makes you think about what that means, this immense structure of stars, gas, dust, and mostly invisible dark matter all held together.
It does. Which leads us to a final thought for you, our listener. With these tighter numbers for the Milky Way's mass and structure, how might that change our ideas about how galaxies like ours form and evolve over cosmic time?
Yeah, and what other cosmic mysteries might these better measurements help us unlock next? It feels like we're just scratching the surface of understanding our place in the universe.
A deep dive that definitely leaves you thinking.